Good morning to all.
Good morning, sir.
Morning, sir.
Yeah,
Good morning, sir.
good morning. I think screen came. PowerPoint presentation is coming to.
Yes, sir.
Yes, sir.
Okay, now I'm going to proceed with the process because in the last week they explained about the state properties at particular state. In the binary fluid system, what we are going to develop as a subsystems of this binary fluid system in a typical poly generation. In the first level, what I did is at a one state, how to read the properties, maybe graphical or analytical. Of course, analytical we are processing now in the process. As per the region, that is 5 regions I classified, and the properties also, the like the temperature, concentration chart, and enthalpy concentration chart it is given. In case fluid is mixture of liquid and vapor, I told the auxiliary curve we have to use, starting from the saturated liquid state, that's at given pressure. At given pressure, of course, the one loop is equal to that's prepared at one particular constant pressure. So based on the pressure and temperature, not the concentration, because the concentration is there are three concentration: mixture concentration, liquid concentration, and vapor concentration. That's why by referring temperature, you may see here the blue lines are the temperature lines. By referring the temperature curves and the pressure, by referring the pressure, we can identify the saturation liquid point. From the saturated liquid state we can draw a vertical line up to the corresponding pressure on the auxiliary curves. Then we have to stop here at the auxiliary curve. We have to stop from auxiliary curve. Once it is meeting the auxiliary curve, we have to change the direction. That is instead of vertical line, horizontal line we have to draw till meeting the saturated vapor curve. Till meeting the saturated vapor curve, and then we have to join the first point, that is the saturated liquid point and saturated vapor point, so that we can get a straight line. That is called as isotherm. That means the temperature of liquid and temperature of vapor and temperature of mixture all are same. How to locate the temperature of the state of the mixture? From the mixture concentration we have to draw a vertical line. This vertical line and isotherm will meet each other. That intersection point is called as liquid mixture, liquid vapor mixture. That's state, because that we are going to use in the process. Because in the process, binary fluid process, the state may be fall any of these regions, like 5 regions. Okay, what type of process we are going to discuss in solving the binary fluid system? It's a thermodynamic process. More or less they are also like single fluid system. A small deviation from the single fluid system is here some additional process we can get it, like separation of the fluid and mixing of the fluid, like absorption process, suppression process, distillation process, or etc. Whereas in the single fluid system, there is no such process, because that is a single fluid only. No need to. There is no need of separation of fluid A and fluid B, or mixing of fluid A and fluid B. But here in the binary fluid system, such process will come. The first one is a separation of fluid A and fluid B, and similarly mixing also. The separation and mixing causes the drive to the working fluid. The separation and the mixing is cause the driving to the working fluid in a cycle, maybe in the cooling cycle or it may be the power cycle. Adiabatic mixing, as per the name, there is no heat, either rejection or absorption. Without heat transfer, if two fluids are mixed with each other, assuming that mixing chamber is completely insulated, then you may call that as adiabatic mixing. But sometimes the mixing process is associated with the heat transfer. It's maybe in the same chamber or it may be separate. Mostly it is the same chamber. Let me take the example of absorber. And since in the BTech mechanical, you are aware about this absorption process. What is the absorption process in the binary fluid system? It looks like a condenser. The difference between the condenser and this absorber is condenser is only heat rejection and getting the saturated liquid state. But here absorption, in addition to the heat rejection, to get the saturated liquid state, the fluids will mix with each other before entering into the condensation. What two fluids? One is a vapor and second is a weak mixture. That's a liquid solutions. Weak mixture is the liquid solutions. So if we are sending the vapor directly into the condensation, it's difficult to condense at the our climatic conditions, the sink conditions, because it needs either high pressure or very low temperature. But without compromising this high pressure, maintaining the high pressure or maintaining the very low temperature in the sink, as usual, like single fluid condensation in this steam power plant, if you are able to dilute the mixture, that's a vapor, before supplying to the condenser, then it is easy. Dilute means more addition of water, so the condensation temperature will increase. The boiling point of H2O is higher than the boiling point of NH3. Once we are keep on adding this water content in the mixture, the boiling point will increase. So no need to maintain the temperature that's close to 0 degrees or 10 degrees, 5 degrees like that. At the temperature of 25, 30, 35, according to the mixing ratio, that's amount of water added into the vapor, we can control the boiling temperature. So in this adiabatic mixing, so mixing takes place to facilitate the heat rejection in the condenser. So that's why adiabatic absorption is a good example for diabatic mixing, where mixing of the fluid takes place, that's liquid and vapor takes place. At the same time, heat rejection also happens for complete condensation of the vapor into the liquid state. So the separation, adiabatic mixing and diabatic mixing, and throttling. This throttling is also similar to the single fluid system. Generally, vapor compression refrigeration system, you studied this throttling process. The fluid is expelled, throttled in a small, narrow, restricted passage. What happens? In thermodynamic point of view, this throttling is also called as, what is the another name of this throttling process according to the thermodynamic process?
Constant
enthalpy.
Same name here also we can give. Binary fluid system also you may call this as isenthalpic, because enthalpy is constant. Here also enthalpy is constant. The deep level of this throttling process is inversion curve, cooling, heating, etc. That's a deep Joule-Thomson effect, etc. In binary fluid system, what our objective is to simulate the exit condition of the throttling device. Because at the inlet of the throttling, we know very well the pressure at what high pressure. At the inlet of the throttling device, that's a high pressure, and the concentration and temperature, that's a PTX. If it is a 1-2 is a process, P1, T1, X1 is supplied. At the exit, we have to simulate the condition. At the exit, obviously the T2 is less than T1 because of the throttling process. Temperature is decreasing. Concentration is same because we are not changing the concentration. The fluid is same, because we are not adding any additional fluid or we are not removing any fluid. That's why concentration is same. Whatever the pressure is decreasing. Since it is expansion, pressure is decreasing. After applying this energy balance equation, the total energy before mixing and after, total energy after total energy before throttling and total energy after throttling, and neglecting sometimes like potential energy, kinetic energy, what you will get, enthalpy is same. And also this insulating, we are assuming there is no heat losses. What we will assume, theoretically what we can assume, enthalpy is constant, that is H1 is equal to H2. So based on this link, that's H1 is equal to H2, we can find the exit temperature either through the chart, what I showed this enthalpy concentration chart, or maybe calculations. Okay, that throttling I will explain in this process for the binary fluid system. Next is the distillation. The meaning of distillation is increasing the concentration. There is one fluid, that's fluid A and fluid B. Our case, the most of the vapor absorption, vapor compression, what fluid we are selecting here? Ammonia water mixture. Of course, lithium bromide water is also is there, but in polygeneration, majority of the cases, we are selecting ammonia water mixture because ammonia water mixture can be used three applications for cooling purpose, power generation purpose, and third is combined cooling and also simultaneous power generation. That's why this fluid has great flexibility, but with some limitations, like at the domestic level it's difficult to use the ammonia because that is toxic means that's a smell, and once we are inhaling, the lungs will affect, respiratory system will problem will come. That's why this mixture is not advisable for the domestic applications. For industrial like cold storage, there is no issue. And also the materials is carefully we have to select, like it's more corrosive for copper and its alloys, bronze, such material. That family we can't use for even bearings, we can't use for this ammonia related working fluid. That's why steel or even mild steel also fine. Some other materials we have to use, but lithium bromide water there is no such issues, like it's not toxic and domestic level we can use. But problem is, as on today I'm saying, lithium bromide water is developed for cooling purpose only. As per the developed technology, what I'm saying is tomorrow may be different, my statement may be wrong. What I'm saying is lithium bromide water mixture is designed and developed for cooling purpose only, not for power generation purpose, not for cooling cogeneration purpose. But we did a small attempt. My students, earlier students, and myself, we studied. Is it possible to develop lithium bromide water mixer for the power generation? Some extent, we got the favorable results. Maybe in future, it will extend for power generation also. That's vapor like Kalina cycle system. We can also develop the lithium bromide water mixer for the power generation. With some limitations are there. That work is going on. Some of the works are reported available in the literature. If you are willing to see the results of this lithium bromide water mixer for power generation, you can browse. You will get some of the information results. Okay, in this distillation, what we are focusing. Okay, there's a NH3 H2O. If the mixture, if you are able to enhance the concentration, that is a NH3 quantity, that is good for cooling, because more amount of NH3 is throttled. What happens? You can get more cooling effect. Of course, the low temperature also, more low temperature will come. That's why, and also finally it will affect the COP. The COP will increase once the concentration increases in the binary fluid system. For that, there is a equipment is also is there, that is called as deflict matter. That is called as deflict matter. Just to, you may recollect it, this deflict matter is used, that's supplied before the condensation. After condensation, it goes to throttling. Once it is throttling, low temperature will come. You can directly send that working fluid to the evaporator. So these three components, that's condensation, throttling, and evaporation. This is common to both vapor compression refrigeration system and also vapor absorption refrigeration system. The remaining components like distillation, separation, absorption, pumping, boiling, that is different. Remaining these three components are same. Okay, in the distillation, we are going to increase the concentration of the fluid so that will favors the cooling system. How it is favoring the power system, that I will explain later. In the analysis level, I will explain. Now this section is only focused on the solutions of the process. So step by step, we can focus on the subsystems and the analysis, and finally the behavior of this process, like distillation process, or the operational conditions, and the performance of the poly generation system. Next is expansion. It's a vapor generation. This vapor generation is like boiler. How to evaluate this boiler system for this vapor absorption refrigeration system, as well as this vapor absorption power system, that's in binary fluid system. This is a process, heat addition process. And condensation, it's a heat sink, heat rejection in the condensation, and vapor expansion in the turbine. In the vapor turbine, the fluid is expanded. How to solve this one? The single fluid system, you studied the isentropic expansion, and after isentropic expansion, by accounting the losses like frictional losses and dissipative effects, we also solved this expansion process for steam turbine and also gas turbine. In gas turbine also, in the earlier semester, we solved the gas turbine power plant, that's gas expansion. Okay. Similarly here, binary fluid, how it will expand in a turbine, it's a vapor turbine, and how to solve the exit condition, how to simulate the exit condition, that is explained here. And pumping, after completion of the condensation, the liquid has to pump to the boiler from low pressure to high pressure. So this solution, mostly strong, in case of vapor absorption refrigeration system, the strong solution we are pumping to the boiler. So that pumping process, the solutions, formulations and solutions of this pumping process is explained here. So this process, that's 1, 2, 3, 4, 5, 6, 7, 8, 9 process. These 9 process, mostly these 9 process is sufficient to understand the behavior of these subsystems like vapor absorption cooling and vapor absorption power systems. Okay. The first one is separation process. Let us say before entry to the condenser in vapor absorption system, or before going to the turbine in vapor binary fluid power system, at the exit of the boiler, most of the cases at the exit of the boiler, the mixture is in the form of liquid vapor condition. Liquid vapor conditions. Without separating, we can't supply this fluid directly to the turbine or directly to the condenser. If you are supplying directly to the condenser, that means sending saturated liquid after separation, I am saying, to the condenser again, that is a waste of material and waste of the process. That's why before supplying to the condenser, the liquid to be separated. And also for turbine, we need to send this vapor only, not the liquid. That's why at the exit of this boiler, in case of recovery, waste heat recovery, that is a heat recovery vapor generator, this component, this is a cylindrical component, is a mechanical component. There is no moving parts. Like even steam power plant also, you can see steam separating drum. In the boiler, you may see the steam separating drum. Similarly, here also looks like, this also looks like a steam separating drum. The mixer from the boiler is entering. This is at the high pressure. Working at high pressure is entering into the separator, where the physical layer, mechanically, the liquid and vapor, by gravity, liquid is collecting at the bottom, and that can be separated. That's a weak solution, since the once you are removing the vapor, that's more ammonia content, then automatically the balanced liquid is less quantity of ammonia. That's why it is called as weak solutions. The weak solution we can use for condensation purpose, because that can be used for diluting the vapor. So easy condensation is possible. That's why that is the advantage of this weak solution. This vapor can be used for either for cooling generation or power generation. So now the process, the solution process, one is separated into 2 and 3. The state 1, see here in the enthalpy concentration chart, state 1 is the liquid vapor mixture, and this is separated to saturated liquid. 2 is a saturated liquid state, and 3 is a saturated vapor state. Graphically, it is easy. That means drawing starting from 1 and identification of the state 2 and state 3, and joining this 2 and 3. This is isotherm process. It's isotherm process. Here we can also use these auxiliary curves to identify these points, like identification of the state 3. For example, at a typical pressure of this P is equal 13 bar, I took this condition from the vapor absorption refrigeration system. This solution is drawn to scale. To solve this problem, in case of analytical solution, we have to prepare the mathematical equations. Graphical means it's simple, directly using pencil and scale. We can identify these states 1, 2, 3 and read the corresponding properties like enthalpy, etc. Okay. It's the formulation, thermodynamic formulation, that separation, M1 is separated into M2 and M3. That's why M1 is equal to M2 plus M3. What about the concentration balance? We know the mass balance. What is meaning of this concentration balance? Concentration balance is called as the ammonia balance. The total quantity of ammonia before separation is equal to total quantity of ammonia after separation. This can be applied to mixing also. The total quantity of ammonia before mixing is equal to total quantity of ammonia after mixing. Yes, this is a equation for ammonia balance. It's this is also like mass balance. This combination of this mass balance and ammonia balance will give the definition of dryness fraction. Of course, without formulating this mass balance and concentration balance, straight away also we can use the dryness fraction. In the last class, I defined the dryness fraction. M1 x1 is equal to M2 x2 plus M3 x3. What is meaning of M1 x1? At state 1, the total quantity of ammonia, actually x1 is defined as, what is the units of this x1? That's concentration, that's number actually. But as per the definition, mass of ammonia per kg mass of mixture, okay.
Mixture.
That's the total mass of mixture, that is a kg. For 1 kg, x1 is a, for 1 kg, for example, if it is x1 is equal to 0.2, what is the meaning of x1 is equal to 0.2? 0.2 kg of ammonia out of 1 kg of mixture. Am I correct? But if m is equal not 1 kg, if m is equal, let us say m1 is equal to 10 kg, what we have to do for total quantity of ammonia? We have to multiply this mass. Am I correct? M1 into x1 gives the total quantity of ammonia. Are you understood this meaning of this M1 X1? X1 is a specific value, kg per kg mixture, 1 kg of mixture. But once you are multiplying this M1, same like specific enthalpy. Let us see specific enthalpy small h. M into h. What is the meaning of M into h? Total enthalpy, capital H. Okay. What is the units of this total enthalpy, capital H? Kilojoules. Kilojoules, not per kilojoules per kg. Are you clear? Similarly here also. X is the specific mass of ammonia, that's we are calling as concentration. Once it is multiplied with this mass, the total mass, you will get the total quantity of ammonia. Are you clear about the meaning of M into X?
Yes.
M into X is the total quantity of ammonia. Similarly, at state 2, the total ammonia is M2X2. At state 3, that's vapor, the total quantity of ammonia is M3X3. So this before separation, the quantity, after separation, the quantity as per the mass balance, this is equal. Simplification of these equations, that means either you can eliminate M2 or you can eliminate M3. Here you have two options. Maybe you will get the definition for dryness fraction or you will get the definition of wetness fraction. That is different. What we are doing here, there are three masses, M1, M2, M3. So in this equation, in the second equation, either you can eliminate the M2 so that it is a function of M1 and M3 only, or you can eliminate M3 so that this function of M1 and M2 only. That means you are combining equation 1 and equation 2. You are combining equation 1 and equation 2, you will get single one equation only. So what is the final simplified equation after this elimination of this M2? M1 X1 is equal, in place of M2, what is M2? M1 minus M3 into X2 plus M3 into X3. The M1 X1 is equal to M1 X2 minus M3 X2 plus M3 X3. Here what we can see, M1 is here and M3 here. M1 into X1 minus X2. Okay, these two terms can be taken out. M1 can be taken out. M1 into X1 minus X2. Right hand side, M3 into X3 minus X2. Okay. Now you can make the mass ratio M1 by M3 or M3 by M1, and mass ratio separate and concentration separates. And mass ratio M3 by M1 is equal, M3 by M1 is equal to X1 minus X2 minus X1 minus X2 by X3 minus X2. X1 minus X2 by X3 minus X2. What is X1? X1 is a mixture, XM. Mixture, I simply keep it as X. X2 is XL. XL means concentration of liquid. X3 is, that is X3. X3 is a XV, concentration of vapor. So X minus XL by XV minus XL. X minus XL by XV minus XL. This is the function, general function I am saying. As per the definition, what is meaning of M3 by M1? As per our regular definition, what we define in the steam power plant. What is meaning of M3 by M1? I define phi or psi, sorry, psi in the last class. It's a df. Here it is showing as df. What is meaning of df? Hello?
Dryness factor.
Dryness section.
Dryness fraction, yeah. The straight away dryness fraction also you may define without clubbing these two equations. In case if you are eliminating M3, you will get wetness fraction. Wetness fraction is defined as M2 by M1, M2 by M1. Now M3 by M1 is equal to x minus xl. Sorry, I will use this one. X1 minus x2, x1 minus x2 by x3 minus x2. What is x1 minus x2? The length of this isotherm, towards the liquid side, from mixer to liquid side. If you take the long scale, measure the distance, how many millimeters, 2 and 3, how many millimeters, and take the length of 1, 2 in millimeter, and take this ratio, the length of 1, 2 by length of 2, 3, that gives the that's a dryness fraction. That gives the dryness fraction. This is according to the lever rule. According to the lever rule, the mass of the vapor is directly proportional to the length of this isotherm towards the liquid side. Length of the isotherm towards the liquid side. Similarly, the mass of the liquid is directly proportional to the length of this isotherm measured from the mixer to vapor or towards the vapor side. Opposite side. Are you observing? This is the length. Opposite side length we are taking. Opposite side length we are taking. That according to the lever rule. That's why this is following the lever rule, similar to the iron carbon diagram what we used in material science and metallurgy. So if you are eliminating M3, what is your final outcome? You will get the wetness fraction. Anybody, could you define the wetness fraction from this explanation? In case if you are eliminating M3, you will result the wetness fraction. Could you define the wetness fraction from lever rule? So in the graphical solution, without doing this simplifications, just straight away by remembering the lever rule, you can calculate the unknown mass or unknown concentration. That's advantage. Anybody, could you define the wetness fraction? I need immediate response. Hello? If you are not responding, I will understood you are not understanding.
Sorry, x3 minus x1 upon x3 minus x2.
Very good, very good. That wetness fraction is equal to x3 minus x1 by x3 minus x2. The total is same. That's M1 is total. That's wetness fraction is defined by M2 by M3. That is equal. The opposite length is x3 minus x1 by the total length is x3 minus x2. The total length is that there is no change. The total mass is directly proportional to the total length. That's not change. But the vapor mass is directly proportional to the liquid side length, and liquid mass is directly proportional to the vapor side length. Okay, I want to ask one logical question. Because the drawing is drawn to scale, I use the MATLAB. This is drawn to scale. Maybe small error. The straight line is okay. A small bend is there. A small fractional error, that is rounding error maybe. My question is the by seeing the relative position, that's 1, 2 and 1, 3. What is the dryness fraction? What is the value of dryness fraction? It's less than 5 or more than 5? Approximately I'm asking. I'm not asking the exact value. We can estimate that by seeing the length, you can see whether dryness fraction is more or less.
Less.
Dryness fraction is less. How you are saying?
Sir, because length between one and
Yeah, this length is too small length. 1, 2 is a small length compared to this length. So after separation, what you will get, this is a actually it's not like process conditions. Just like that, I didn't selected this process conditions. I selected the process conditions from the plant. That's why this explanation I'm applying to the units also, subsystems also. If it is like a textbook problem, is I can't convey this information to the subsystems, to the poly generation. That's why this example is taken from the subsystems only. What I'm saying is, after the boiler, you can get a small amount of vapor only, a small quantity of vapor only. Don't expect the more quantity, like more than 50% of the vapor you can generate, and that you can use for refrigeration or power plant. Not like that. It's small quantity of vapor only you can generate, and more amount of liquid is recycled. More amount of liquid is recycled. That's why my point of view, what I can say is there is a lot of scope to improve this vapor quantity by modifying the existing technology. Now you can see the scenario of vapor absorption refrigeration system, the configuration of this vapor absorption refrigeration system, or configurations of this power plants like binary fluid power plants such as the Kalina cycle system. There is a more scope to improve these configurations or the layout so that you can generate more amount of vapor. Once you are able to generate more quantity of vapor, then it's easy to, you can easily generate more cooling effect as well as more power generation, which may support the poly generation. This is my imagination only. Just those who are interested, you can proceed further in future developments. So now this slide is defining the drainage fraction of the fluid. That's psi, the symbol df or psi we can use. Yeah. If I am giving the drainage fraction, value of drainage fraction, how to calculate the x? How to calculate the x from given x2 and x3? X is equal, could you simplify this line? X is equal, I don't have the digital pad actually. Anybody, x is equal to, write the equation. X is equal to, as a function of XL, XV and drainage fraction.
So drainage fraction into XV minus XL plus XL.
Very good. I think we use this equation, I think so, nearly. X is equal to XL plus psi into or df into XV minus XL. Okay.
Yes, sir.
Even single fluid system also, like enthalpy, H is equal to HL plus drainage fraction is X in the steam power, X into HV minus HL. Am I correct? Specific entropy, specific enthalpy, exergy. We did like this. So here we can find this concentration, the concentration from this drainage fraction value. Not only concentration, it's you can find the enthalpy of this mixer and entropy of the mixer. That's energy as well as exergy we can calculate from this drainage fraction. Same like what you are seeing here. X is equal to XL minus 5 into XV minus XL. Here H is equal to HL minus psi into HV minus HL. As specific entropy also same. Those equations you can. This is vice versa, is showing this wetness fraction. The wetness fraction M2 by M1 is equal to XV minus X, XV minus XL. This is M2. M2 is this one. That means X3 minus X1, opposite side length. Okay, now how to extend this explanation to the other properties? This is mass balance equation. Okay, if you are same like mass balance, if you are generating the energy balance or exergy balance, we can get the results for the finding the enthalpy or entropy. See here, energy balance is showing here M1 H1 is equal M2 H2 plus M3 H3. That means total energy before separation is equal to total energy after separation. After eliminating M2 or M3, what you will get here? If I am eliminating M2, M1 H1 is equal to M1 minus M3 H2 plus M3 H. Same like concentration. M1 H1 is equal to M2 H2 minus M3 H2 plus M3 H3, and simplification, M is taken out, M1 into H1 minus H2, right side M3 is taken out, M3 into H3 minus H2. Therefore, M3 by M1. M3 by M1 is equal, again this M3 by M1 is a psi, that is a dryness fraction. But this dryness fraction we are defining in terms of enthalpy. Earlier dryness fraction is same for all the cases. Dryness fraction is defined as a function of concentration. The x-axis here is a concentration. The same dryness fraction you can also define by y-axis, that is enthalpy. This is also following the lever rule. That's M3, the vapor is directly proportional to enthalpy of this mixer and liquid side, H minus HL, and total length is directly proportional to total mass is directly proportional to HV minus HL. Or in terms of numbers, H1 minus H2 by H3 minus H2. And wetness fraction also you may define similarly. Wetness fraction also you can define in terms of enthalpy. So what the conclusion is here, once you know the dryness fraction, if you are able to calculate the dryness fraction in the numerical problems, it is easy to calculate the unknowns. Maybe mixer may be unknown or liquid may be unknown, and you can solve this suppression process easily by using a lever rule, either in graphical form or in the analytical form. Graphical form means you need the chart and pencil, long pencil I am saying, long pencil and scale, sorry, scale and pencil. Because long scale is more useful because the gap between the auxiliary curves and liquid is more. If you see this is actually drawn to one particular pressure only, but once you are combining all the pressures, the length of the chart will increase. That's why you have to use the scale, proper scale. Short scale may not be sufficient. So this XL is equal to X2 plus dryness fraction into X3 minus X2. Similarly, in terms of enthalpy also you can define. So that is about this formulation of this separation process. Mixing process, more or less it is same. It's opposite. Actually, mixing is the opposite. Separation means A, B you separated physically. Mixing means the two fluids A and B is mixed together. What happened here? Sorry, this is not updated. This is separation I am showing. I will change this figure. Let me show the mixing. Okay, there are two fluids, 1 and 2 has been mixed together, and you got the mixer at 3. One thing here I want to show, separation and mixing process. Separation means that's completely, after separation you are saying the completely saturated liquid and saturated vapor. But mixing, we can't say like this. Before mixing there is a freedom. The one may be subcooled saturated liquid or liquid vapor mixer. It may be superheated vapor, saturated vapor. And 2 also. The 2 may be liquid, saturated vapor, superheated vapor, whatever it may be. That any fluid, Mr. X, Mr. X1 and Mr. X2, we are combining together. Whereas in separation means we are separating according to the process, the binary fluid process, we are separating to saturated liquid and saturated vapor. Mixing is not like that. Okay, that's why the solution for separation is more easy compared to the solution of this adiabatic mixing process. In this adiabatic mixing process, we didn't consider the heat transfer. That's why you can show this process as a straight line. If it's a heat transfer, you can't see a straight line. That's non-linear lines or curves will come. And what about this thermodynamic formulation? That's mass balance and energy balance. Mass balance is M1 plus M2 is equal to M3, and concentration balance is M1 X1 plus M2 X2 is equal to M3 X3. And energy balance, M1 H1 plus M2 H2 is equal to M3 H3. These are the 3 equations, balance equations I am saying: mass balance, concentration balance, and energy balance. So continuation of this simplification of these equations, that is elimination of either M2 or M3, either M2 or M3, because our focus is here. After mixing, the exit condition we have to simulate. Exit condition we have to simulate that. X3 we have to calculate. H3 we have to calculate. That's why X3 is equal. That's why X3 is equal from this earlier equations after this elimination, M1 X1 plus M2 X2 by M3. 1 minute, I will show this earlier equations. I refer these old equations. Okay, now what I'm saying is eliminating M2. Eliminating M2 in this second equation, what you will get here in place of M2, what you will get? M2 is equal to M3 minus M1. M2 is equal to M3 minus M1. So you can get here this 1 and 2 only. That's sorry, 2 is eliminated here. M3 minus M1. M3 minus M1, because this second equation we focus here. X3 is equal to M1 X1 plus M2 X2 by M3. In place of M2, we are writing M3 minus M1. That means M3 X2 minus M1 X2. M1 by M3. Where is here? Is there any cancellation here? M1 X1, M3 X1. X2. Yes. See here X2 term. M3 gets cancelled. Okay. So the left out is X2. And what about the X1 and X2? M1 you can take it out. M1 here is here also. M1 is there. If you are taking out M1 out, X1 minus X2 divided by M3. Are you clear about this equation? X3 is equal to X2 plus M1 by M3 into X1 minus X2. M1 by M3 is the ratio, mass ratio. X1, X2. In this, according to this drawing, X1 minus X2. It is showing X1 minus X2 is negative. Okay. X1 minus X2 is negative. That's why if you want to write this X2 minus X1, we have to keep minus. So according to this drawing, X3 is equal to X2 minus M1 by M3 into X2 minus X1. So finally, the simplified equation is M1 by M3 is equal to M1 by M3 is equal to X3 minus X2 by X2 minus X1. X2 minus X1. Is it clear or is there any mistakes here?
There will be one negative sign in front of M1 by M3.
Sign convention, some sign conventions, I think so.
Yes, sir. Negative
Okay.
sign in front of M1 and
Okay. I will correct this one. What M1 by M3 is, M1 is here, M3 is here, and 3, 2, and 2, 1. 2, 1 is a total. And this is more or less, I can say, the explanation of earlier what we applied for the separation. This is also following the lever rule. Am I correct? This is also following the lever rule. I will explain after these corrections because the drawing I had to update. Tomorrow I will continue. Okay. I had reversed this one. This is a separation is showing. After doing this correction, tomorrow I will continue this mixing process as well as heat transfer process. Okay.
Okay, sir.
Okay, sir.
Next week, are you coming next week?
No,
Not
sir.
now, sir.
Hmm?
No, sir.
No.
So we are not sure yet because we live far, and if the condition worsens, then we have to come back again
How is the
like
condition?
last time.
Same. Repeat. May repeat. I think so. Yeah.
Yes, sir. That is, sir. Like last time, we had to hurry so back.
Yeah, you came for 1 month. I think so.
Yes, sir.
Yes, sir.
My book it is updated. Actually, PowerPoint presentation it's not updated. It's adiabatic mixing. Yes, yes, yes. It's fine. Okay, I will update the presentation, PPT presentation. Why I'm asking is if you are coming here, I can give you the book so that you can take some copy or something. But soft copies are not available. Don't leave. I have to take the attendance. As a copyrighted edited, that's why they are not sharing the soft copy. I think you this semester also maybe more or less maybe online. Are you expecting?
Yes, sir.
Okay, I will do one thing. Today I uploaded the IIT Kharagpur material. Just you can download the PDF files and you may prepare this IIT Kharagpur material. That's nice material actually. That's nice material. Even though uh, mine is mostly applications. That basics you can read the basics thoroughly. What to explain these basics of the process and basics of the properties that you may refer. Even IIT Kharagpur the material also. Basics is same all. Okay, fine. 1 minute. Please. Number 2.
Present, sir.
3,
Yes, sir.
4,
Present, sir.
5,
Present, sir.
6,
Yes, sir.
7, 8,
Present, sir.
10, 11,
Present, sir.
12,
Present, sir.
13,
Yes, sir.
21, 221,
Yes, sir.
14, 214,
Present, sir.
1 minute. I have some net problem. Yes, okay, you may leave.
Okay, thank you, sir.
Thank you, sir.
Okay,
Thank you, sir.
Thank you, sir.
thank you.
Hello, sir.
Yes, yes. Hello, hello. Hello? Hello? Hello, somebody calling?
So it was okay, so he left.
Okay, fine.